Now what we're going to do is start setting these equations equal to each other for kinetic and gravitational potential energy and looking at what happens when you go from one form to another. So just as a refresher, since we're going to be using them often, the equation for kinetic energy is 1/2 mv squared, and the equation for gravitational potential energy is mgh. So what we're going to do when we solve, you're going to set your initial energy equal to the final energy. So you're going to look at a problem. You're going to figure out what type of energy it has initially. You're going to set that equal to what type of energy it ends up with. And then you may see problems where something's going on in the middle as well. We'll set that equal. So energy at A equals energy at B equals energy at C. We're going to use bar charts to identify each type of energy at every part of the problem. You're going to write out all the equations. Once you figure out what type of energy you have, cancel any variable in all terms. This is usually going to be mass. Mass will usually not matter. And then you're going to solve. So let's just do an example and see how they work. You've seen this already. This looks just like the one from the energy bar charts because it was copied and pasted, but I added some numbers. So you have a pendulum of mass 2 kilograms swinging from a height of 0.2 meters to the base level at point B. How fast is it moving when it reaches the bottom? So let's make our energy bar charts. You already know what these look like because I did them with the examples for energy bar charts. You start with no kinetic energy and all gravitational potential energy. When it gets to the base level, it's moving, but no longer has height. So we have all kinetic energy. This is A, and this is B. So your energy at A equals your energy at B. Again, I just like to do this because it's visual. It's easier for me to identify and relate to the bar charts. The type of energy I have at A is gravitational potential energy, and that's going to equal the type of energy I have at B, which is kinetic energy. And then we write out the equations. So your gravitational potential energy equation, mgh, equals your kinetic energy, 1/2 mv squared. Most of the time for these problems, mass will cancel because it's in every term. So gh equals 1/2 v squared. G is a constant. It gives us the height. Mass was irrelevant. We did not need that. And now we can solve for V. So 9.8 meters per second squared times 0.2 meters equals 1/2 v squared. 9.8 times 0.2, 1.96. This ends up being meters squared per second squared equals 1/2 v squared. Multiply both sides by 2 so that v squared is by itself. 3.92 meters squared per second squared equals v squared. That's v squared, not v. So we need to take the square root. 1.98 meters per second is the speed. So it's not super fast, but pendulum starts from a height of 0.2 meters, and when it gets to the bottom, it'll be moving 1.98 meters per second. It does not matter how massive that pendulum was because the mass canceled in this step. So any object starting from a height of 0.2 meters will be moving about 2 meters per second once it gets to the ground. All right, let's do another example. Now we have a 1 kilogram cart moving at 4 meters per second. What height does it come to rest? So A and B, base level is the ground. At A it's moving, it has no height. At B, it has height. It is no longer moving. Energy at A equals energy at B. This time, it's kinetic energy at A equaling gravitational potential energy at B. 1/2 mv squared equals mgh. Mass cancels. So 1/2 of 4 meters per second squared equals g, 9.8 meters per second squared times height. 4 squared is 16. Half of 16 is 8. 8 meters squared per second squared equals 9.8 meters per second squared times the height. Divide both sides by 9.8 meters per second squared. 8 divided by 9.8 is 0.816 meters. So your height is about equal to 0.82 meters. Once again, all you're doing for these problems is setting the types of energy equal to each other and then solving for whatever is unknown. Okay, I'll do the last one, and this one has 2 types of energy when we get to B. Car is moving, rolls up a hill, and we want to know how fast it's moving at that height of 0.3 meters. So making the ground the base level once again, you're going to start with kinetic energy at A, no gravitational at A. At B, it's both moving and has height. Energy at A equals energy at B. Kinetic energy at A equals kinetic energy plus gravitational potential energy at B. 1/2 mv squared equals 1/2 m. This is my v at B squared. So there are 2 v's, they are not the same. Plus mgh. Mass cancels. 1/2 v squared equals 1/2 vb squared. And if it helps, you can put a little a here to remind you that this would be your speed at A. Again, they are not the same speed. Plus gh. So 1/2 of 4 meters per second squared equals 1/2 vb squared plus 9.8 meters per second squared times 0.3 meters. Half of 4 squared, so 4 squared is 16, half of that is 8 meters squared per second squared equals 1/2 vb squared plus 9.8 times 0.3, 2.94 meters squared per second squared. I'm going to subtract the 2.94 from both sides. And I get 5.06 meters squared per second squared. Multiply both sides by 2. 10.12 meters squared per second squared equals VB squared. Square root both sides. 3.18 meters per second is the speed when it's at that height of 0.3 meters. This is probably as complicated as it will get. You will never have more than 2 types of energy that you need to worry about at one spot. So it's either moving, it's either at a height, or it is moving with a height above the base level. If you have a problem where there is a part C, so if you were looking at something even more in the middle, or let's say you continued this problem and you looked at where it got to the top, all you're doing is setting another equality. So with the conservation of energy problems, everything is always going to be equal. The only 2 equations we're using are 1/2 mv squared and mgh. And the tricky things, there's 2 of them. 1, remembering to take the square root if you're solving for speed, or square it if you're using that. And the second tricky thing is if you have 2 different speeds, just to make sure that you are not making them the same. So if it's moving at 2 different parts of the problem, you need to account for the 2 different speeds.